Let's do some example problems. So let's recall our main equations. Here, Kev, keep your mask on, Hunter. We have Ohm's law, which I remember is there. And we have energy is equal to power times time. So, stop that. So we have power. Its units is a watt, which is equivalent to joules per second. We have current. Its unit is the ampere, usually abbreviated as amp. We have resistance. Unit is the ohm. Keep your mask on. Voltage is the unit volt. And we have energy. Its unit is the joule. Equivalently, a joule is equal to a watt times a second. Stop squishing on the water bottles. These are the base units for most of the year, except for like the first test that we have. I've been sticking to the base units, but when we get to energy, it's often more useful to talk about kilowatt hours. Because when it comes to electricity, the amount of energy in electricity is quite a lot. So if you wanted to convert 1 kilowatt hour into joules, so a joule is equal to a watt second, so we need to convert kilowatt hours into watt seconds. So we multiply by 1. So let me actually expand this out. So 1 kilowatt hour, and then we'll multiply this by, well, I know that there is 1,000 watts in 1 kilowatt. So kilowatt cancel out, which gives me watt hours. I multiply this by get hours. There is 3,600 seconds in 1 hour. So hours cancel out, and we're left with watts and seconds. So 1 kilowatt hour is equal to 1,000 times 3,600. So that's 3,600,000 watt seconds. And a watt second is the same thing as a joule. So 1 kilowatt is equal to 3.6 million joules. Keep your mask on. So let's do an example problem. A 40 watt light bulb is connected to 120 volts for 8 hours. How much current is pushing through the light bulb? So what will the equation be? Which equation will we use? So we're given power and we're given voltage. We're also given time. So we have power and voltage and we're looking for current. So this is going to use power is equal to current times voltage, which we can make a nice triangle from. Power is equal to current times voltage. Current is thus power over voltage. So 40 watts divided by 120 volts, and that's 0.333 so on amps. Yeah, Steve, sit over there. Tyler, she's constantly turning around and looking at you. You can ask your teacher. Resistance, what we've been doing all year, or all unit. It's the resistance of a resistor. It's the R variable. So, what is the resistance of the light bulb? So which equation will we use for this? Well, we have to use an equation that has R in it. So Ohm's law, we know voltage is equal to current times resistance. So resistance is equal to voltage over current. So our voltage is 120 volts. For current, we previously saw for, yes, I suppose. So 120 volts divided by basically a third of an amp, dividing by a fraction is the same as multiplying by the reciprocal. So 120 times 3 is 360 ohms. What is the total energy? In kilowatt hours. So energy is power times time. To get it in kilowatt hours, or power must be in kilowatts, and our hours, our time, must be in hours. Or time was 8 hours, so we already have time in hours. But our power is given as 40 watts. 40 watts is the same as 40 divided by 1,000 kilowatts. The K and the 1,000 cancel each other out to give you the watts. And that's the same thing as 0.04 kilowatts. So energy is equal to 0.04 kilowatts times our 8 hours. And that's equal to 0.32 kilowatt hours. If we wanted to solve for the energy in joules, we do the same thing. What is the total energy in joules? You just need to know that joules is the same thing as watt seconds. So we need our power in watts and our time in seconds. Our equation for energy is equal to power times time, where power is 40 watts, or time, so 8 hours. To convert into seconds, we can multiply by 60 minutes per hour. That cancels out the hours and gives us minutes. And then multiply by 60 seconds in 1 minute. That cancels out minutes. So that gives us seconds left. So 8 times 60 times 60, which is 28,800 seconds, giving us a total of 1,152,000 watt seconds, which we can replace watt seconds with joules. You can see why kilowatt hours is preferred over joules, because these are very large numbers. If you're curious about doing conversions like this, is 1 hour the same as 60 minutes? So what is anything divided by itself? 1. And if you multiply by something by 1, does it change? So multiplying 8 hours by 1 is still 8 hours. But the hours in here cancel each other out, leaving us just minutes. So 60 minutes divided by 1 hour is just 1. It's a fancy way of writing 1. 60 seconds divided by 1 minute, since you're dividing two things that are the same thing, it's just 1. And 1 times anything is still the same thing. The only thing we're doing is getting rid of the units. Yes. I suppose. A 12-volt car battery supplies 2 amps of current to a car's headlamp or headlight for 3 hours. You never driven on the road for over 3 hours? Well, we can actually calculate and see if that would happen. I don't think a car would die in 3 hours. Bad battery. That's actually a very good point. I can actually show you, as it's very easy using this information, how to figure out how long a battery will power something before it dies. So calculate the power consumed by the car's headlight. So we know power is current times voltage. Our current is 2 amps. Our voltage is 12 volts. So 2 amps times 12 volts. That's 24 watts. So if we're in base units, if as long as we're not in milliamps or kilovolts or anything like that, as long as it's amp times a volt, power is watts. So that's another thing I should indicate. A watt is equal to an amp times a volt. So 1 watt is equal to 1 amp times 1 volt. So that's the power. Calculate the resistance of the headlight. So this is resistance is going to correspond to Ohm's law. Voltage is equal to current times resistance. Resistance is thus volts over current. So that would be 12 volts over 2 amps, which gives us 6 ohms. How much energy in joules does the headlight use? Energy is equal to power times time. We want it in joules, so we want this in watts, and that's in seconds. So we calculate the power. The power is 24 watts. And we need to convert 3 hours into seconds. So I'm going to multiply by 1. The one I'm choosing is 3,600 seconds over 1 hour. There are 3,600 seconds in 1 hour. Hours cancel out. Which is equal to 10,800 seconds. So we plug it in for time. KP, stay awake. That's what seconds.
Paul O'Brien, come to the office, please. Paul O'Brien.
And what second is the same thing as joule. We could have also calculated it in kilowatt hours by doing the same thing, except for we're going to convert power into kilowatts. So 24 watts times there is 1 kilowatt and 1,000 watts. So watts cancel out, giving us just kilowatts. So that's equal to 24 divided by 1,000 kilowatts, which is equal to 0.024 kilowatts. So plug that in. AP, lift your head up. So 0.072 kilowatt hours. Yep. So a 50 ohm resistor is connected to a 5-volt battery for 10 minutes. How much power is dissipated?
Excuse me for a quick interruption, students. The proof orders are in Furniture Woods. They will be here till 5 o'clock this evening. So those of you who sold fruit need to make sure and make arrangements to come out there and get your things picked up to deliver to the people who sold. Thank you.
How much power is dissipated by the resistor? Dissipated is a word that just means to remove energy by generating heat. Heat is considered useless. So I'm going to give you a formula sheet. Power can be solved for in various different ways. If we're given current and voltage, power equals current times voltage. If we're just given voltage and resistance, it's voltage squared over resistance. If you're given current and resistance, it's current squared times resistance. This is from combining Ohm's law. So looking at that formula sheet, I saw that power is voltage squared over resistance. Our voltage is 5, so we square it. Divide by 50. That's equal to 25 over 50. So 0.5 watts. How much current is flowing through the resistor? So current is equal to voltage over resistance. Our voltage is 5 volts. Our resistance is 50 ohms. And that's equal to 0.1 amps. We could have also solved for power by using power is current times voltage. The current solved right here, 0.1 amps. And that times the voltage of 5 volts also gives you 0.5 watts. So how much thermal energy is generated by the resistor? Energy equal to power times time. Power, 0.5 watts. For time is 10 minutes. But to do energy, we need power in watts and time in seconds. So multiply this by the conversion factor, 60 seconds in 1 minute. Minute in the numerator, a minute in the denominator. Cancel each other out. So that's 600 seconds. Which gives us 300 joules. Doesn't produce very much heat. Keep your mask on, Hunter. I have a question for you guys. So, does a refrigerator run constantly? So, we're going to calculate here in a little bit how much it would cost you to run a refrigerator constantly. But a refrigerator doesn't run constantly. The reason for this is usually it's set to some temperature. You have a knob inside your refrigerator. You have cold and warm, or some scale between it. You have like colder and cold, and you switch over, and that's the temperature your refrigerator will shut off at. So if you set it to like 40 degrees, it'll cool it down to like 39, 40 degrees, and it'll shut off. Then it'll warm up to like 43, 45, and it'll turn back on and cool it back down until it gets down to like somewhere between 38 and 40. It averages about 40 degrees Fahrenheit. Why does it warm up? Or I should say this. Let's say that we have a freezer. More talking about the freezer. So we have a freezer like this, where the door opens outward, versus a deep freezer, where the door opens up like this. Which one do you think better, or which one do you think uses more electricity? A giant big deep freezer, or your kitchen freezer? A small vertical one versus a flat horizontal one. And this could be very big, and this could be somewhat small. Which do you think uses less energy? Which one uses less? Have you ever opened up the freezer or refrigerator for a second and then close it and immediately hear it kick on? Why is that? So hot rises, right? But cold also falls. When you open this refrigerator, all the air inside of it is cold. But it's going to immediately fall out to the ground. And warm air is going to rush in to fill that void. Actually, due to the fact that as air cools, it compresses or shrinks, you might try to open the refrigerator about 10 seconds later and it didn't open. That's because it creates a partial little vacuum, but the pressure difference dropped. But what happens when you open up a deep freezer? Cold sinks to the bottom. All the cold air, as long as you don't open it super fast, all the cold air stays in there. So this one actually, every time you open it, removes all the cold air from inside of it. Alan, lift your head up so you can see. So what would happen if you are the type of person where you go, I'm hungry, and you go to the refrigerator, open it up, look inside, close it, couldn't find anything to eat. 5 minutes later, you go back, open it up again, look to see, close it. 10, 30 minutes later, you go back in, and even though you looked at it multiple times, if you are that type of person, you might notice you have a slightly higher electrical bill as you're basically making the refrigerator stay on constantly. Try not to open the refrigerator as much. Also, if the electricity goes out, you should not open the door of your refrigerator. If you might do it at the very beginning, but in the moment you open it, all the hot air is going to go in, and then eventually it's going to cool down and warm up everything inside. And if you keep doing it, you can very quickly warm up the inside of your refrigerator. So let's calculate what would happen if you left it on 24/7. So a refrigerator is connected to a 110 volt line and uses 5 amps of current. So the power that's dissipated, by the way, if you open up the refrigerator and keep your mask on, if you open up the refrigerator, turn it on, first of all, most refrigerators, the light switch at the bottom usually cuts it off. A lot of refrigerators, the moment you open it, it cuts the refrigerator off so it's no longer running, to prevent the door from accidentally being opened and having it run there doing nothing. There are some refrigerators that won't shut itself off when you open it, but imagine you had one that where you could open it and it'll start running. Would it make the room warmer or colder? A refrigerator is a generator of heat. It generates heat. It takes heat from inside and warms it up and then pushes it outside. That's the reason behind the refrigerator is very hot. During the process of moving the air from inside to outside, it actually heats that air up significantly. So the power that is dissipated, meaning lost due to heat by the refrigerator, we can solve that by P equals IV. The current is 5 amps. The voltage is 110 volts. That's 550 watts. We can calculate the resistance too. We could use Ohm's law or the other equation. So if we use Ohm's law, resistance is equal to volts over current. That's 110 volts over 5 amps, which is equal to 22 ohms. And stop messing with the bottle. Or we could do that resistance is equal to power over current squared. So yes. No. Or do it real quick. Pull it. So 5 squared. That's also 22 ohms. And we could have even gone R equals V squared over power. Same thing. That's 110 squared over 550. That's also 22 ohms. No matter which equation you choose, as long as you plug in the correct values, it works. So what is the energy used if it ran for 30 days straight? So for this, we want kilowatt hours. So the power is 0.55 kilowatts. The time, so 30 days, there are 24 hours in one day. So that's 720 hours. And that gives us 396 kilowatt hours. And let's use 12 cents for East Texas per kilowatt hour. So the cost would equal 396 kilowatt hours times the ratio of 12 cents for 1 kilowatt hour. Kilowatt cancels, leaving us dollars. That's equal to $47.52 to run a refrigerator for a month. If you don't open it as much, it can get down to costing you $50 a year, or even less. Some of them can get down to $25 a year.
Formula G. Giving an idea. I got stuff to deliver when I get home.
And now here's your homework.
Oh my goodness. We got stuff to do when we get home. From the school. Mr. West. We got stuff to do. Looks like it's done now.
Right.
11 questions with 3 marks.
Can you write that?
Oh, our man is trying to find
Yeah, this might not be done or might not be given to you.
not give out homework.
What grade is he in? Great. No, you didn't.
Really?
No.
Keep your mask on. I'll let y'all work on it in class tomorrow.
Friday? Friday?
Monday.
Yes.
No.
My dad can do it. Let's go. Guess what? I ain't gonna be at home Friday.
We'll work on it tonight and tomorrow.
Well, tonight I gotta deliver stuff.
I'm not doing it.
I mentioned it. I was gonna lie to you.